Imagine a universe where everything, every star, planet, and living being came from nothing. This idea goes against what we know and pushes the limits of our understanding. Atoms, the tiny building blocks of all matter, are key to this big mystery. But if atoms came from nothing, what created this nothing? This question blends science and philosophy, making us rethink what existence really means. As we explore the origins of atoms and the realm of nothingness, we start a journey that could change how we see the universe and our place in it. Atoms and their formation. First, we must understand atoms. Atoms, the fundamental units of matter, are the very essence of the physical universe. These tiny particles, invisible to the naked eye, constitute everything we see, touch, and experience in our daily lives. From the air we breathe to the stars that light up the night sky, atoms are the building blocks that form the tapestry of the cosmos. An atom is the smallest unit of an element that retains the properties of that element. Each atom is composed of a nucleus, containing positively charged protons and neutrally charged neutrons, surrounded by a cloud of negatively charged electrons. The number of protons, known as the atomic number, defines the type of element. For instance, an atom with one proton is hydrogen, the simplest and most abundant element in the universe. The structure of atoms is governed by fundamental forces. The strong nuclear force binds protons and neutrons together in the nucleus, overcoming the repulsive force between positively charged protons. Meanwhile, the electromagnetic force ensures that electrons remain in orbit around the nucleus. These forces work in harmony, creating a stable entity that forms the foundation of all matter. The story of atoms begins in the moments following the Big Bang, the event that gave birth to our universe approximately 13.8 billion years ago. In the first few minutes, the universe was an incredibly hot and dense environment, composed primarily of fundamental particles such as quarks and gluons. As the universe expanded and cooled, these particles began to combine, forming protons and neutrons. This period, known as nucleosynthesis, occurred within the first few minutes after the Big Bang. During this time, the first atomic nuclei were formed, predominantly hydrogen and helium, along with trace amounts of lithium and beryllium. These light elements became the building blocks for more complex atoms. While the early universe provided the initial batch of light elements, it is within the hearts of stars that the formation of more complex atoms occurs. Stars act as cosmic furnaces, where nuclear fusion processes create heavier elements from lighter ones. In the core of a star, intense pressure and temperature conditions allow hydrogen nuclei to fuse together, forming helium and releasing vast amounts of energy in the process. This energy powers the star and sustains its luminosity. As stars evolve, they undergo various stages of fusion, producing elements such as carbon, oxygen, and silicon. The heaviest elements, like iron, are formed in the final stages of a star's life cycle. When a massive star exhausts its nuclear fuel, it undergoes a cataclysmic explosion known as a supernova. This explosion disperses the star's enriched material into space, seeding the interstellar medium with heavy elements. These remnants can eventually coalesce to form new stars, planets, and ultimately, the diverse array of matter we observe today. While the processes of atomic formation are well understood, the question of the ultimate origin of atoms, and by extension the universe itself, remains a profound mystery. What triggered the Big Bang? What existed before it? These questions delve into the realms of cosmology and theoretical physics, challenging our understanding of the fundamental nature of reality. One prevailing theory suggests that the Big Bang was not the absolute beginning, but rather a transition from a previous state of existence. Concepts such as the multiverse hypothesis propose that our universe is just one of many, each with its own set of physical laws and properties. In this framework, the Big Bang could be a recurring event, part of an endless cycle of creation and destruction. Another line of inquiry involves the concept of quantum fluctuations. At the smallest scales, governed by quantum mechanics, the vacuum of space is not empty but teeming with virtual particles and fluctuations. Some theorists posit that a quantum fluctuation could have sparked the Big Bang, giving rise to our universe from a sea of potentiality. The quest to understand the nature and origin of atoms is a testament to human curiosity and our desire to comprehend the universe. From the ancient Greek philosophers who first speculated about indivisible particles to the cutting-edge research conducted in particle accelerators today, the journey of discovery has been long and arduous. Scientific advancements have provided remarkable insights into the atomic world. The development of quantum mechanics and particle physics has unveiled the intricate dance of subatomic particles. Technologies such as electron microscopes and particle colliders have allowed us to probe the very fabric of matter, revealing the hidden complexities of atoms. Early atomic models and quantum mechanics. The journey to understand the atom, the fundamental building block of matter, has been one of the most intriguing and revolutionary chapters in the history of science. From the early 20th century's puzzling experimental results to the advent of quantum mechanics, the evolution of atomic models showcases humanity's relentless pursuit of knowledge and the profound shifts in our understanding of the universe. In the early 1800s, John Dalton proposed the first modern atomic theory, suggesting that elements were composed of indivisible atoms and that each element's atoms were unique. This idea laid the groundwork for future discoveries, but the true complexity of atomic structure remained hidden for another century. The discovery of the electron by J.J. Thomson in 1897 marked a significant milestone. Thomson's experiments with cathode rays revealed the existence of negatively charged particles much smaller than atoms, challenging the notion of indivisibility. He proposed the plum pudding model, envisioning atoms as spheres of positive charge embedded with negatively charged electrons. Although this model was soon proven incorrect, it was a crucial step in developing atomic theory. The next leap came in 1911 with Ernest Rutherford's gold foil experiment. Rutherford and his colleagues bombarded a thin gold foil with alpha particles and observed the scattering patterns. Most particles passed through the foil, but some were deflected at large angles. This unexpected result led Rutherford to propose a new model. Atoms consisted of a tiny, dense, positively charged nucleus surrounded by electrons. Rutherford's nuclear model solved many puzzles but also raised new questions. According to classical physics, electrons orbiting the nucleus should continuously emit radiation, losing energy and spiraling into the nucleus. This implied that atoms should be inherently unstable. Yet matter was known to be stable. This paradox set the stage for further developments. In 1913, Niels Bohr, a Danish physicist, introduced a groundbreaking model that resolved the stability issue. Drawing inspiration from quantum ideas, Bohr proposed that electrons could occupy only certain discrete orbits or energy levels around the nucleus. These orbits were quantized, meaning electrons could not exist between them. Electrons could move between these orbits by absorbing or emitting energy in the form of photons. Bohr's model explained the spectral lines observed in hydrogen atoms. When an electron transitioned from a higher energy level to a lower one, it emitted a photon with a specific wavelength, corresponding to the energy difference between the levels. This accounted for the discrete spectral lines seen in hydrogen's emission spectrum. Bohr's theory was a monumental advancement, yet it had limitations. It worked well for hydrogen, but struggled to accurately describe more complex atoms. Despite this, Bohr's model laid the foundation for the development of quantum mechanics and profoundly influenced our understanding of atomic structure. The early 20th century witnessed the emergence of quantum mechanics, a new framework that revolutionized physics. Quantum mechanics addressed the inadequacies of classical physics and provided a comprehensive description of atomic and subatomic phenomena. Max Planck's work on blackbody radiation and Albert Einstein's explanation of the photoelectric effect introduced the concept of quantization of energy. Planck proposed that energy is emitted or absorbed in discrete units, called quanta. Einstein extended this idea to light, suggesting that light consists of particles, or photons, each carrying a quantized amount of energy. In 1924, Louis de Broglie proposed that particles, such as electrons, exhibit both wave-like and particle-like properties. This wave-particle duality was confirmed by experiments and became a cornerstone of quantum mechanics. De Broglie's hypothesis led to the development of wave mechanics by Erwin Schrödinger, who formulated the famous Schrödinger equation. This equation describes how the quantum state of a system evolves over time and provides a probabilistic view of atomic behavior. Werner Heisenberg, another key figure in quantum mechanics, introduced the uncertainty principle in 1927. Heisenberg's principle states that it is impossible to simultaneously know both the precise position and momentum of a particle. This inherent uncertainty arises from the wave-particle duality and fundamentally limits the precision of measurements. The uncertainty principle challenged classical deterministic views and underscored the probabilistic nature of quantum mechanics. It implied that at a fundamental level, the behavior of particles is governed by probabilities rather than definite paths. This shift in understanding marked a profound departure from classical physics and redefined our conception of reality. Quantum mechanics provided a robust framework for understanding atomic structure. The Schrödinger equation allowed scientists to calculate the probability distributions of electrons around the nucleus, known as atomic orbitals. These orbitals describe regions in space where electrons are likely to be found, offering a more accurate representation of atomic behavior than Bohr's orbits. Quantum mechanics also introduced the concept of electron spin, a fundamental property that affects an electron's behavior in magnetic fields. The Pauli exclusion principle, formulated by Wolfgang Pauli, stated that no two electrons in an atom could occupy the same quantum state simultaneously. This principle explained the structure of the periodic table and the arrangement of electrons in different energy levels. The development of early atomic models and the advent of quantum mechanics marked a transformative era in science. These breakthroughs not only resolved long-standing mysteries, but also opened new avenues of research and technology. Quantum mechanics has since become the foundation of modern physics, underpinning fields such as condensed matter physics, quantum chemistry, and particle physics. Max Planck's quantization of radiation. The story of modern physics is marked by profound revelations that have transformed our understanding of the universe. Among these, Max Planck's quantization of radiation stands as a pivotal breakthrough. This discovery not only laid the foundation for quantum mechanics, but also significantly influenced Niels Bohr's groundbreaking work on atomic structure. Together, their contributions ushered in a new era of scientific thought, challenging classical paradigms and revealing the mysterious world of the quantum. In the late 19th century, physicists grappled with a perplexing issue known as the blackbody radiation problem. A blackbody is an idealized object that absorbs all radiation falling on it and re-emits energy across a range of wavelengths. Classical physics, based on Maxwell's equations and thermodynamics, could not accurately predict the observed spectrum of blackbody radiation, especially at higher frequencies. This discrepancy, known as the ultraviolet catastrophe, suggested that classical theories were incomplete. In 1900, Max Planck, a German physicist, made a revolutionary proposal to resolve the blackbody radiation problem. Planck suggested that energy is not emitted or absorbed continuously, as classical physics assumed, but rather in discrete packets called quanta. He introduced the idea that the energy of these quanta is directly proportional to the frequency of the radiation, with the proportionality constant now known as Planck's constant. Planck's quantization hypothesis can be summarized by the equation E equals hv, where E is the energy of the quantum, h is Planck's constant, and v is the frequency of the radiation. This groundbreaking proposal resolved the ultraviolet catastrophe by limiting the amount of energy that could be emitted at higher frequencies, aligning theoretical predictions with experimental observations. Planck's work marked the birth of quantum theory, challenging the classical continuum view of energy and introducing a fundamentally new way of understanding the physical world. Building on Planck's quantum hypothesis, Albert Einstein further advanced the understanding of light and energy. In 1905, Einstein explained the photoelectric effect, a phenomenon where light striking a material surface ejects electrons from that surface. Classical wave theory could not adequately explain the observed characteristics of the photoelectric effect, such as the immediate ejection of electrons and the dependence of electron energy on light frequency. Einstein proposed that light itself is quantized into discrete particles, later called photons, each carrying a quantum of energy E equals hv. This particle nature of light was a radical departure from the classical wave theory and provided strong support for Planck's quantization of energy. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921 and cemented the concept of quantization in the burgeoning field of quantum mechanics. Niels Bohr, a Danish physicist, was deeply influenced by the emerging quantum theories of Planck and Einstein. In 1913, Bohr applied the concept of quantization to the structure of the atom, developing a model that resolved several inconsistencies in atomic theory. Bohr proposed that electrons orbit the atomic nucleus in specific, quantized energy levels, or shells, rather than in arbitrary paths as suggested by classical physics. According to Bohr's model, an electron in a given orbit does not radiate energy. It only emits or absorbs energy when transitioning between these quantized orbits. The energy difference between these orbits corresponds to the energy of the emitted or absorbed photon. This model elegantly explained the discrete spectral lines observed in hydrogen's emission spectrum, where electrons jump between quantized energy levels, emitting or absorbing photons with specific energies. Bohr's theory accounted for the stability of atoms, resolving the paradox of why electrons do not spiral into the nucleus as classical physics predicted. The hydrogen atom, the simplest atom with only one electron, provided a crucial testing ground for Bohr's model. Bohr's quantized orbits explained the series of lines in the hydrogen spectrum known as the Balmer series, which classical physics could not. Max Planck's introduction of quantized energy levels was instrumental in Bohr's development of his atomic model. Planck's quantization principle provided the theoretical foundation that Bohr needed to explain atomic stability and the discrete nature of atomic spectra. Without Planck's pioneering work, Bohr might not have arrived at his revolutionary model that bridged classical and quantum physics. Planck's and Bohr's contributions collectively transformed our understanding of the microscopic world. Planck's quantization of radiation solved the blackbody radiation problem and introduced the concept of discrete energy levels, while Bohr's application of quantization to atomic structure provided a coherent explanation for atomic spectra and stability. The collaboration between Planck's theoretical framework and Bohr's atomic model marked the beginning of a new era in physics. Their work paved the way for the development of quantum mechanics, a theory that would revolutionize science and technology in the 20th century and beyond. Quantum mechanics, developed in the 1920s and 1930s by pioneers such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, extended the principles introduced by Planck and Bohr. The Schrödinger equation, Heisenberg's uncertainty principle, and Dirac's relativistic quantum theory provided a comprehensive and unified framework for understanding atomic and subatomic phenomena. Today, the legacy of Planck's quantization and Bohr's atomic model continues to influence diverse fields, from chemistry and materials science to information technology and quantum computing. The principles they uncovered have led to technological advancements such as lasers, transistors, and MRI machines, profoundly impacting modern life. Advanced atomic theory. The journey to comprehend the fundamental structure of matter has been marked by continuous evolution and refinement of atomic models. From the early 20th century discoveries that led to the quantum revolution to the sophisticated models of today, our understanding of atomic structure has deepened, revealing the intricate and fascinating behavior of electrons. The early atomic models, such as Dalton's solid sphere model and Thomson's plum pudding model, laid the groundwork for later discoveries. Rutherford's nuclear model introduced the concept of a dense nucleus surrounded by electrons. But it was Niels Bohr's model in 1913 that incorporated quantization, providing a breakthrough in explaining atomic stability and spectral lines. However, Bohr's model, which depicted electrons in fixed orbits around the nucleus, was soon found to be insufficient. It could accurately describe the hydrogen atom but failed to generalize to more complex atoms. The need for a more comprehensive theory led to the development of quantum mechanics, fundamentally altering our understanding of atomic structure. One of the most revolutionary concepts introduced by quantum mechanics is the wave-particle duality of electrons. This idea was proposed by Louis de Broglie in 1924, suggesting that particles such as electrons exhibit both wave-like and particle-like properties. De Broglie's hypothesis was initially met with skepticism, but experimental evidence soon confirmed this duality. The famous double-slit experiment, first conducted with light and later with electrons, demonstrated this dual nature. When electrons were fired at a barrier with two slits, they produced an interference pattern characteristic of waves rather than the pattern expected of particles. This experiment provided compelling evidence that electrons could behave as waves, leading to a paradigm shift in our understanding of atomic and subatomic particles. Building on de Broglie's hypothesis, Erwin Schrödinger formulated the wave equation in 1926, known as the Schrödinger equation. This equation describes how the quantum state of a physical system changes over time, providing a mathematical framework for understanding the wave-like behavior of electrons. The Schrödinger equation treats electrons as standing waves or wave functions around the nucleus. These wave functions, denoted by the Greek letter psi, represent the probability distributions of finding an electron in a particular region of space. Instead of fixed orbits, as in Bohr's model, electrons occupy orbitals, regions where the probability of finding an electron is high. The solutions to the Schrödinger equation for the hydrogen atom revealed a set of quantum numbers, each corresponding to different properties of the electron orbitals. These quantum numbers describe the unique state of an electron in an atom, allowing for the detailed configuration of electrons in multi-electron atoms. The Pauli exclusion principle, formulated by Wolfgang Pauli, states that no two electrons in an atom can have the same set of quantum numbers, explaining the arrangement of electrons in different orbitals. The concept of standing wave patterns is crucial in understanding electron orbitals. In classical physics, a standing wave is a wave that remains in a constant position, characterized by nodes, points of zero amplitude, and antinodes, points of maximum amplitude. In the context of quantum mechanics, standing wave patterns describe the allowed states of electrons in an atom. Origin of atoms and the universe. The quest to understand the origin of atoms and the universe is a profound scientific endeavor, stretching the boundaries of human knowledge. At the heart of this exploration lies the Big Bang theory, which provides the most widely accepted explanation for the birth of the universe and the formation of the first atoms. This narrative will take us through the timeline from the initial singularity through the inflationary epoch to the formation of stable atoms and the evolution of the cosmos. The Big Bang theory posits that the universe began as an infinitely small, hot, and dense singularity approximately 13.8 billion years ago. This singularity contained all the mass and energy that would become the universe. The concept of the Big Bang was first proposed by Belgian priest and physicist Georges Lemaitre in the 1920s, and it was later supported by observational evidence, such as the discovery of the cosmic microwave background radiation and the expansion of the universe observed by Edwin Hubble. The Planck epoch marks the very beginning of time, a period so short that our current physical theories cannot fully describe it. During this epoch, the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, are thought to have been unified. The temperature was unimaginably high, and the universe was a seething sea of energy. As the universe expanded and cooled, it transitioned into the Grand Unification epoch. During this time, gravity separated from the other fundamental forces. The strong nuclear force remained unified with the electroweak force, a combination of the electromagnetic and weak nuclear forces. This epoch ended with the separation of the strong nuclear force. One of the most critical phases in the early universe is the inflationary epoch. Proposed by Alan Guth in the 1980s, the theory of cosmic inflation suggests that the universe underwent an exponential expansion, growing by a factor of at least 102610 circumflex, 261026, in a fraction of a second. This rapid expansion smoothed out any irregularities, leading to the homogeneous and isotropic universe we observe today. During inflation, quantum fluctuations were stretched to macroscopic scales, seeding the large-scale structure of the universe. These fluctuations would later grow into galaxies, clusters of galaxies, and the cosmic web. Following inflation, the universe continued to expand and cool, leading to the separation of the electro-weak force into the electromagnetic and weak nuclear forces. This period is marked by the formation of the Higgs field, which gave mass to elementary particles through the Higgs mechanism. As the universe cooled further, it entered the quark epoch. During this time, the temperature was still too high for quarks to bind together to form protons and neutrons. The universe was a hot, dense plasma of quarks, gluons, and other elementary particles. When the universe cooled to below 1 trillion degrees Kelvin, quarks began to combine, forming protons and neutrons. This transition marked the beginning of the Hadron epoch. Most of the antimatter annihilated with matter during this time, leaving a slight excess of matter, which would become the building blocks of the universe. Following the Hadron epoch, the universe entered the Lepton epoch. During this time, leptons such as electrons and antileptons dominated the mass of the universe. As the universe continued to cool, these particles began to annihilate each other, leaving a slight excess of electrons and other leptons. After the Lepton epoch, photons dominated the universe. However, the universe was still too hot for electrons to combine with protons to form neutral atoms. Photons continuously scattered off free electrons in a process known as Thomson scattering, keeping the universe opaque. At around 380,000 years after the Big Bang, the universe cooled sufficiently for protons and electrons to combine, forming neutral hydrogen atoms in a process called recombination. This era marks the formation of the first stable atoms. As electrons bound to protons, photons could travel freely without scattering, leading to the decoupling of matter and radiation. The photons released during this period still travel through the universe today as the cosmic microwave background radiation, a faint afterglow of the Big Bang. Following recombination, the universe entered the Dark Ages, a period lasting until the formation of the first stars and galaxies. During this time, the universe was composed mainly of neutral hydrogen and helium atoms, with no sources of light. Around 100 million years after the Big Bang, regions of slightly higher density began to collapse under their own gravity, forming the first stars known as population 3 stars. These stars were massive, short-lived, and responsible for producing the first heavy elements through nucleosynthesis. The death of these stars, often in supernova explosions, seeded the universe with heavier elements and led to the formation of subsequent generations of stars and galaxies. The radiation from the first stars and galaxies reionized the neutral hydrogen in the universe, ending the Dark Ages and allowing the universe to become transparent to ultraviolet light. This period, known as the Epoch of Reionization, was crucial for the formation of large-scale structures. Over the next billions of years, gravity continued to pull matter together, forming larger and more complex structures. Galaxies merged to form clusters and superclusters, creating the vast cosmic web we observe today. The universe's expansion, driven by dark energy, continues to accelerate, shaping the future of cosmic evolution. Fundamental forces and subatomic particles. The universe is governed by a set of fundamental forces and composed of subatomic particles that form the very essence of matter. Understanding these forces and particles is crucial for unraveling the mysteries of the cosmos, from the smallest scales of particle physics to the grand structure of galaxies. This narrative explores the 4 fundamental forces: gravity, weak force, electromagnetism, and strong force, delving into their roles and the subatomic particles they influence. Gravity is perhaps the most familiar of the fundamental forces, yet it is the weakest in terms of strength. It is the force of attraction between masses, governing the motion of planets, stars, galaxies, and even light. Described by Isaac Newton's law of universal gravitation and later refined by Albert Einstein's general theory of relativity, gravity operates over infinite distances, shaping the large-scale structure of the universe. Einstein's theory revolutionized our understanding by describing gravity not as a force, but as a curvature of space-time caused by mass and energy. Massive objects like stars and planets distort the fabric of space-time, creating gravitational wells that other objects fall into. Despite its weakness compared to other forces, gravity's reach and influence are pervasive, affecting the entire cosmos. Electromagnetism is the force responsible for electric and magnetic phenomena. It is significantly stronger than gravity and operates between charged particles. Described by James Clerk Maxwell's equations, electromagnetism unifies electricity and magnetism into a single theory. This force is responsible for the behavior of electrons in atoms, the transmission of light, and the forces between magnets. Electromagnetic force operates over infinite distances but diminishes with the square of the distance between charges. It governs a wide range of phenomena, from the chemical bonds that hold molecules together to the technology enabling communication and power generation. The weak nuclear force, or weak interaction, is responsible for processes like beta decay and radioactive elements. It is stronger than gravity, but weaker than electromagnetism and the strong nuclear force. The weak force operates at very short ranges, on the order of 10 to the power of -18 meters, affecting subatomic particles like quarks and leptons. This force is mediated by the exchange of W and Z bosons, particles that are much heavier than the photons of electromagnetism. The weak interaction is crucial for the synthesis of elements in stars and the balance of particles in the universe, playing a key role in the processes that fuel the Sun and other stars. The strong nuclear force, or strong interaction, is the most powerful of the fundamental forces, operating at extremely short ranges, roughly 10 to the power of -15 meters. It is responsible for binding protons and neutrons together in atomic nuclei, overcoming the electromagnetic repulsion between positively charged protons. The strong force is mediated by particles called gluons, which act as the carriers of the force between quarks. This interaction is described by the theory of quantum chromodynamics, QCD, which explains how quarks are held together by gluons to form protons, neutrons, and other hadrons. The strong nuclear force is essential for the stability of atomic nuclei. Without it, the repulsive electromagnetic force between protons would cause nuclei to fly apart. This force binds quarks together to form protons and neutrons, and subsequently binds these nucleons into nuclei, creating the diverse elements of the periodic table. In a nucleus, the strong force acts over short distances to hold protons and neutrons tightly together. This force is not constant, but increases as quarks are pulled further apart, a phenomenon known as confinement. At very short distances within the nucleus, the strong force is attractive and much stronger than the electromagnetic repulsion, ensuring nuclear stability. The energy associated with the strong nuclear force is immense, as evidenced by the energy released in nuclear reactions such as fission and fusion. In fission, the splitting of heavy nuclei releases a tremendous amount of energy, while fusion, the combining of light nuclei, powers stars and holds potential for future energy sources on Earth. Quarks are the fundamental constituents of protons and neutrons. They come in 6 flavors: up, down, charm, strange, top, and bottom. Protons are composed of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. Quarks are held together by the strong nuclear force, mediated by gluons. Gluons are massless particles that carry the strong force, binding quarks together through the exchange of force. Unlike photons in electromagnetism, gluons themselves carry color charge, leading to a complex interaction network described by QCD. This interaction ensures that quarks are never found in isolation, a property known as confinement. Instead, they exist in bound states such as protons, neutrons, and other hadrons. QCD is the theory that describes the strong interaction. It posits that quarks carry a type of charge called color charge, which comes in 3 types: red, green and blue. Gluons, which mediate the strong force, carry a combination of these color charges. The force between quarks is strongest when they are close together and increases as they move apart, ensuring quarks remain confined within hadrons. The QCD interaction is also responsible for the generation of most of the mass of protons and neutrons. While the individual masses of quarks are small, the energy of the strong interaction between them contributes significantly to the mass of nucleons, illustrating the profound impact of the strong force on the material universe. The four fundamental forces and the particles they influence form the foundation of the universe's structure and behavior. Gravity shapes the cosmos on the largest scales, governing the motion of galaxies and the formation of cosmic structures. Electromagnetism dictates the behavior of charged particles, enabling the formation of atoms and molecules essential for life. The weak nuclear force facilitates nuclear reactions in stars, contributing to the synthesis of elements and the balance of matter in the universe. The strong nuclear force ensures the stability of atomic nuclei, enabling the diversity of elements and the complexity of matter. Together, these forces and particles create the intricate tapestry of the universe, from the smallest scales of subatomic particles to the vast expanse of cosmic structures. Understanding these fundamental components allows us to comprehend the nature of reality, the origins of matter, and the forces that drive the evolution of the cosmos. The study of fundamental forces and subatomic particles reveals the intricate and interconnected nature of the universe. Gravity, electromagnetism, the weak nuclear force, and the strong nuclear force each play distinct and crucial roles in shaping the cosmos. Quarks and gluons, the building blocks of protons and neutrons, interact through the strong force to form the nuclei of atoms, while the interplay of all fundamental forces governs the behavior and evolution of matter. As we delve deeper into the nature of these forces and particles, we uncover the fundamental principles that underpin the universe. Size and stability of atoms. The measurement of atomic and subatomic dimensions has long intrigued scientists, particularly when it comes to the size of the proton, a fundamental constituent of atomic nuclei. In recent years, the proton radius puzzle has emerged as a significant enigma in physics. Measurements of the proton's size have produced conflicting results, challenging our understanding of fundamental physics and prompting a re-examination of established theories. The size of a proton is typically measured using methods such as electron scattering and spectroscopy of hydrogen atoms. Electron scattering involves firing high-energy electrons at protons and analyzing the deflection patterns to infer the proton's size. Spectroscopy, on the other hand, examines the energy levels of hydrogen atoms, which are influenced by the proton's charge distribution. These methods have historically provided consistent results, but discrepancies have arisen in recent measurements. In 2010, a team of researchers using muonic hydrogen, a type of hydrogen where the electron is replaced by a much heavier muon, found the proton radius to be significantly smaller than previous measurements. This unexpected result, known as the proton radius puzzle, has sparked considerable debate and investigation. Muonic hydrogen allows for more precise measurements due to the muon's closer orbit around the proton, amplifying the effects of the proton's charge distribution. The discrepancy between measurements from muonic hydrogen and traditional methods remains unresolved, suggesting possible gaps in our understanding of quantum electrodynamics or the need for new physics beyond the standard model. The stability of atoms is a cornerstone of matter's persistence over time. Atoms consist of a dense nucleus of protons and neutrons, surrounded by a cloud of electrons. The forces holding these components together are fundamentally stable, ensuring that most atoms remain unchanged for vast periods. Protons and neutrons in the nucleus are bound by the strong nuclear force, one of the four fundamental forces of nature. This force is incredibly powerful over short distances, effectively counteracting the repulsive electromagnetic force between positively charged protons. Electrons are bound to the nucleus by the electromagnetic force, with negatively charged electrons attracted to the positively charged protons. This attraction stabilizes the atom, preventing electrons from drifting away. However, the exact arrangement of electrons around the nucleus described by quantum mechanics, determines the chemical properties of each element. While atoms are generally stable, they can undergo transformations under certain conditions. One of the most well-known processes affecting atomic stability is radioactive decay, where unstable nuclei spontaneously change into different nuclei. This process is governed by the interplay of nuclear forces and is characterized by the emission of particles or electromagnetic radiation. Radioactive decay occurs in several forms, including alpha decay, beta decay, and gamma decay. Alpha decay involves the emission of an alpha particle, 2 protons and 2 neutrons, resulting in the transformation of the original atom into a new element with a lower atomic number. Beta decay involves the transformation of a neutron into a proton or vice versa, accompanied by the emission of a beta particle, an electron or positron, and a neutrino. Gamma decay involves the release of excess energy from an excited nucleus in the form of gamma radiation. A critical concept in radioactive decay is the half-life, the time required for half of the atoms in a sample of a radioactive substance to decay. Half-life is a statistical measure that reflects the probabilistic nature of decay as individual atoms decay at random times. Each radioactive isotope has a characteristic half-life ranging from fractions of a second to billions of years. For example, uranium-238, a common isotope in nature, has a half-life of approximately 4.5 billion years, making it a useful tool for dating geological formations. The stability of atoms and their components over time is a balance between the forces that hold them together and the processes that can disrupt this equilibrium. While protons and neutrons within stable nuclei are bound tightly by the strong nuclear force, certain isotopes are inherently unstable due to the ratio of protons to neutrons. This instability leads to radioactive decay, a process that not only transforms elements, but also releases energy that has practical applications in fields such as medicine, energy production, and scientific research. In addition to natural radioactive decay, human activities can induce nuclear reactions that affect atomic stability. Nuclear fission, for instance, involves the splitting of heavy atomic nuclei into smaller fragments, releasing a substantial amount of energy. This principle underlies nuclear reactors and atomic bombs. Conversely, nuclear fusion, the process powering stars, involves the merging of light nuclei to form heavier ones, also releasing energy. Efforts to harness fusion for energy production are ongoing, promising a potentially limitless and clean energy source if technological challenges can be overcome. The study of atomic stability extends beyond practical applications to the fundamental understanding of matter and the universe. The proton radius puzzle, for instance, highlights the intricacies of subatomic interactions and the limitations of current theories. Resolving this puzzle may require new theoretical frameworks or more precise experimental techniques, potentially leading to groundbreaking discoveries in particle physics. The exploration of atomic and subatomic phenomena continues to be a dynamic field of scientific inquiry, driven by the quest to understand the building blocks of matter. Advances in technology, such as particle accelerators and sophisticated detectors, enable researchers to probe deeper into the nature of atomic stability and the forces that govern it. These investigations not only expand our knowledge of the microcosm, but also shed light on the fundamental principles that shape the macroscopic universe. As we delve further into the mysteries of atomic size and stability, we are reminded of the intricate and interconnected nature of the physical world. From the puzzling measurements of the proton radius to the profound implications of radioactive decay, the study of atoms reveals a rich tapestry of phenomena that underpin the structure and behavior of matter. The ongoing pursuit of knowledge in this field promises to uncover new insights and deepen our appreciation of the fundamental forces and particles that constitute the fabric of reality. Interactions and molecular formation. The formation of molecules from individual atoms is a fundamental process that underpins the diversity and complexity of the material world. Atoms interact through various mechanisms to form chemical bonds, resulting in the creation of molecules with distinct properties and behaviors. These interactions are governed by principles of quantum mechanics, electron configurations, and energy states, all of which play crucial roles in determining the nature of chemical bonding. At the heart of molecular formation is the concept of the chemical bond. Chemical bonds are the forces that hold atoms together within a molecule, allowing them to achieve greater stability. There are several types of chemical bonds, each characterized by different interactions between the participating atoms' electrons. One of the most common types of chemical bonds is the covalent bond. Covalent bonding occurs when two atoms share one or more pairs of electrons. This sharing allows each atom to attain a more stable electron configuration, often resembling the electron configuration of noble gases. For example, in a molecule of water, H2O, each hydrogen atom shares an electron with the oxygen atom, resulting in a stable arrangement where the oxygen atom has a full outer shell of electrons. The nature of covalent bonds can vary, with single, double, or triple bonds forming depending on the number of shared electron pairs. Single bonds involve one pair of shared electrons, double bonds involve two pairs, and triple bonds involve three pairs. The strength and length of these bonds differ, with triple bonds being the shortest and strongest, and single bonds being the longest and weakest. Another fundamental type of chemical bond is the ionic bond. Ionic bonding occurs when one atom donates an electron to another, resulting in the formation of oppositely charged ions. These ions are held together by the electrostatic attraction between their opposite charges. Ionic bonds typically form between atoms with significantly different electronegativities, such as sodium and chlorine in sodium chloride, NaCl. In this compound, sodium donates an electron to chlorine, resulting in a positively charged sodium ion, Na+, and a negatively charged chloride ion, Cle. In addition to covalent and ionic bonds, there are metallic bonds which occur in metals and involve a sea of delocalized electrons that move freely throughout the metallic lattice. This type of bonding explains many of the characteristic properties of metals, such as electrical conductivity and malleability. The formation of chemical bonds is intimately linked to the energy states of atoms. Atoms strive to reach a state of lower energy, which often corresponds to a more stable configuration. When atoms form chemical bonds, energy is either released or absorbed, depending on the nature of the interaction. This exchange of energy is a key factor in determining the stability of the resulting molecule. In covalent bonding, the shared electrons occupy molecular orbitals, which are regions of space where the probability of finding the shared electrons is highest. These molecular orbitals are formed from the overlap of atomic orbitals, which are the regions of space associated with individual atoms' electrons. The formation of bonding molecular orbitals results in a lower energy state, contributing to the stability of the molecule. Electron configurations also play a crucial role in molecular formation. The electron configuration of an atom describes the distribution of its electrons among the available energy levels and orbitals. The arrangement of electrons determines how an atom can interact with other atoms and form bonds. Atoms with incomplete outer electron shells, such as hydrogen, oxygen, and carbon, are particularly prone to forming chemical bonds to achieve a stable electron configuration. Valence electrons, the electrons in the outermost shell of an atom, are the primary participants in chemical bonding. The number of valence electrons determines an element's bonding behavior and its position in the periodic table. Elements in the same group of the periodic table have similar valence electron configurations and exhibit similar chemical properties. For example, carbon has 4 valence electrons and can form 4 covalent bonds with other atoms to achieve a stable octet configuration. This tetravalent nature of carbon is the basis for the vast diversity of organic compounds, including those that make up living organisms. Energy states in atoms and molecules are quantized, meaning that electrons can only occupy specific energy levels. The transitions of electrons between these levels involve discrete amounts of energy. When an electron in an atom absorbs energy, it can be excited to a higher energy level. Conversely, when an electron falls to a lower energy level, it releases energy, often in the form of light. This principle of quantized energy states is fundamental to understanding chemical reactions and spectroscopy. In spectroscopy, the interaction of light with matter provides insights into the energy levels of electrons in atoms and molecules. Each element and molecule has a unique spectral signature, allowing scientists to identify substances and study their properties. Molecular formation is not just about the formation of bonds between atoms, but also about the resulting molecular geometry. The spatial arrangement of atoms within a molecule affects its properties and reactivity. VSEPR, valence shell, electron pair repulsion theory, is a model used to predict the geometry of molecules based on the repulsion between electron pairs in the valence shell. For instance, the tetrahedral geometry of methane, CH4, results from the repulsion between 4 pairs of bonding electrons around the central carbon atom. Similarly, the bent shape of water, H2O, arises from the 2 lone pairs of electrons on the oxygen atom, which repel the bonding pairs and create a nonlinear structure. Intermolecular forces, which are forces between molecules, also play a critical role in determining the physical properties of substances. These forces include hydrogen bonding, dipole-dipole interactions, and London dispersion forces. Hydrogen bonding, a strong type of dipole-dipole interaction, occurs when hydrogen is bonded to highly electronegative atoms like oxygen, nitrogen, or fluorine. This interaction is responsible for the unique properties of water, such as its high boiling point and surface tension. Dipole-dipole interactions occur between molecules with permanent dipoles, where the positive end of one molecule is attracted to the negative end of another. London dispersion forces, the weakest of the intermolecular forces, arise from temporary fluctuations in electron distribution, creating momentary dipoles that induce attractions between molecules. Understanding how atoms interact and form molecules, the nature of chemical bonds, and the influence of electron configurations and energy states provides a comprehensive picture of the molecular world. These principles are fundamental to chemistry and essential for exploring the complexities of biological systems, materials, science, and the universe itself. Through the study of atomic and molecular interactions, we gain insights into the building blocks of matter and the forces that shape the physical world. Macroscopic and microscopic perspectives. In the vast expanse of the universe, the behavior of matter can be understood through 2 distinct but interconnected lenses, the macroscopic and the microscopic perspectives. These perspectives allow us to explore and comprehend the complexities of atomic and subatomic behavior, offering insights into the fundamental nature of reality. To grasp the intricate world of atoms and subatomic particles, analogies often serve as valuable tools. One common analogy compares atoms to tiny solar systems, with electrons orbiting the nucleus much like planets orbit the Sun. While this analogy captures the general structure, it falls short in describing the true nature of atomic interactions. Unlike planetary orbits, electron paths are governed by the principles of quantum mechanics, leading to behaviors that defy classical intuition. Consider another analogy, the atom as a cloud. This analogy better captures the probabilistic nature of electron positions. Instead of fixed orbits, electrons exist in regions of space called orbitals, where they are most likely to be found. This cloud-like distribution arises from the wave-like properties of electrons, a concept rooted in quantum mechanics. These analogies, while imperfect, provide a bridge to understanding the seemingly abstract behavior of subatomic particles. At the atomic level, interactions between atoms determine the properties of matter. When we touch an object, such as a table or a piece of metal, we perceive its solidity. However, this sensation of solidity is an emergent property arising from interactions at the atomic level. Atoms are mostly empty space, with a dense nucleus surrounded by a cloud of electrons. The solidity we experience results from the electromagnetic forces between these electrons. When you press your hand against a surface, the electrons in the atoms of your hand repel the electrons in the atoms of the surface. This repulsion is due to the Pauli exclusion principle, which states that no 2 electrons can occupy the same quantum state simultaneously. This principle, along with the electromagnetic force, prevents the atoms in your hand from passing through the atoms in the surface, creating the sensation of touch and solidity. Quantum mechanics plays a pivotal role in the behavior of atoms, and by extension, the solidity of objects. One of the fundamental principles of quantum mechanics is wave-particle duality. which states that particles such as electrons exhibit both wave-like and particle-like properties. This duality is central to understanding atomic interactions. Electrons in an atom occupy discrete energy levels or orbitals. These energy levels are quantized, meaning electrons can only exist in specific states with defined energies. The arrangement of electrons in these orbitals determines the chemical properties of the atom and how it interacts with other atoms. When atoms come close together, their electron clouds overlap, leading to the formation of chemical bonds. Quantum mechanics also introduces the concept of electron probability densities. Instead of following precise paths, electrons exist in a probabilistic manner, described by wave functions. These wave functions provide the likelihood of finding an electron in a particular region around the nucleus. This probabilistic nature underlies the electron cloud model, where electrons form diffuse clouds rather than distinct orbits. The interactions between atoms and the formation of chemical bonds are governed by quantum mechanical principles. Covalent bonds, for example, involve the sharing of electron pairs between atoms. These shared electrons occupy molecular orbitals, which are formed by the overlap of atomic orbitals. The stability and strength of these bonds arise from the lowering of the energy state when electrons are shared, leading to a more stable configuration. Another quantum mechanical phenomenon essential to understanding atomic interactions is the exchange interaction. This interaction is crucial for the stability of molecules and materials. In simple terms, the exchange interaction is a quantum effect that arises due to the indistinguishability of electrons and their tendency to avoid each other, contributing to the overall stability of the atomic arrangement. The solidity of objects at the macroscopic level emerges from the cumulative effect of countless atomic interactions. The collective behavior of atoms, governed by quantum mechanics, results in the properties we observe and experience daily. The rigidity of a solid object, the flexibility of a liquid, and the diffusiveness of a gas all stem from the underlying quantum mechanical interactions between atoms and molecules. Furthermore, quantum mechanics explains the thermal properties of materials. Atoms in a solid vibrate around their equilibrium positions, and these vibrations are quantized as phonons. The distribution of these vibrational states determines the material's thermal conductivity and specific heat capacity. The transfer of energy through these quantized vibrations illustrates how quantum mechanics influences macroscopic properties. One of the most striking examples of quantum mechanics' impact on macroscopic behavior is superconductivity. Superconductors are materials that exhibit zero electrical resistance below a certain temperature. This phenomenon arises from the formation of Cooper pairs, where electrons pair up and move through the material without scattering. This pairing is a quantum mechanical effect that leads to the macroscopic property of superconductivity, enabling applications such as magnetic resonance imaging, MRI, and maglev trains. Understanding atomic and subatomic behavior through analogies, exploring touch and interaction at the atomic level, and recognizing quantum mechanics' role in the solidity of objects highlights the profound interconnectedness of the microscopic and macroscopic worlds. Quantum mechanics provides the framework to comprehend the behavior of atoms, the formation of molecules, and the emergence of material properties. Atoms and color. The concept of color at the atomic level is a fascinating intersection of physics, chemistry, and perception. Atoms and molecules interact with light in complex ways, leading to the vivid array of colors we observe in the world around us. Understanding these interactions requires delving into the principles of reflection, absorption, and thermal radiation, which collectively govern how matter displays color. Color arises from the interaction of light with matter. Light is an electromagnetic wave, and its different wavelengths correspond to different colors in the visible spectrum, ranging from violet, with the shortest wavelengths, to red, with the longest wavelengths. When light encounters an object, it can be reflected, absorbed, or transmitted, and the interplay of these processes determines the color we perceive. At the atomic level, color is fundamentally linked to the electronic structure of atoms and molecules. Electrons in an atom occupy specific energy levels. and these levels are quantized, meaning that electrons can only exist in certain discrete states. When light strikes an atom, its energy can be absorbed by an electron, causing the electron to jump to a higher energy level. This absorption depends on the wavelength, or color, of the light, and the specific energy levels of the electrons in the atom. Different materials have unique sets of energy levels, which means they absorb and reflect light differently. For instance, a material that absorbs most wavelengths, except for those corresponding to red, will appear red to our eyes. This is because the red wavelengths are reflected or transmitted, while the other colors are absorbed. Reflection is one of the key processes in color perception. When light strikes a surface, some of it is reflected back. The nature of this reflection depends on the surface's properties at the atomic level. In metals, free electrons can move easily and interact with the incident light, causing it to reflect efficiently. This is why metals often have a shiny, reflective appearance. The specific wavelengths of light that are reflected determine the color of the metallic surface. In contrast, non-metallic surfaces reflect light differently. When light hits such a surface, it may penetrate a short distance before being reflected. The interaction between the light and the atoms or molecules in the material can cause certain wavelengths to be absorbed and others to be reflected. This selective absorption and reflection give non-metallic objects their color. For example, leaves appear green because chlorophyll molecules absorb blue and red light, reflecting green light. Absorption of light at the atomic level is closely tied to the concept of electronic transitions. When an atom or molecule absorbs light, an electron is promoted to a higher energy level. The energy difference between these levels must match the energy of the absorbed photon. This is why different substances absorb different wavelengths of light. For example, the pigment melanin in human skin absorbs ultraviolet, UV, light, protecting deeper tissues from its harmful effects, and in doing so, it imparts color to the skin. Thermal radiation is another crucial aspect of how atoms and molecules interact with light. All objects emit radiation due to the thermal motion of their atoms and molecules. This emission, known as blackbody radiation, depends on the temperature of the object. At higher temperatures, objects emit more radiation at shorter wavelengths. For example, a heated iron rod will glow red, then orange, and eventually white as its temperature increases due to the emission of thermal radiation across the visible spectrum. At the atomic level, thermal radiation occurs because the atoms and molecules are in constant motion. As they move, they accelerate and decelerate, causing them to emit electromagnetic radiation. The spectrum of this radiation depends on the temperature, with hotter objects emitting more high-energy, shorter wavelength radiation. The color of an object due to thermal radiation can be explained by Planck's law, which describes the distribution of radiation emitted by a blackbody at a given temperature. The phenomenon of fluorescence also demonstrates how atoms and molecules can influence color. Fluorescence occurs when a substance absorbs light at one wavelength and then re-emits it at a longer wavelength. This process involves an electron being excited to a higher energy level by the absorbed light, then losing some energy through non-radiative processes before falling back to a lower energy level and emitting a photon. The emitted light typically has a lower energy, longer wavelength than the absorbed light, resulting in a shift in color. Fluorescent dyes and minerals are common examples, where absorbed UV light is re-emitted as visible light in various colors. Phosphorescence is similar to fluorescence but involves a longer timescale for the re-emission of light. In phosphorescent materials, the absorbed energy can be trapped in a metastable state, causing the material to continue glowing even after the initial light source is removed. This prolonged emission is due to the energy being slowly released over time, which can be seen in glow-in-the-dark materials. In addition to these processes, the interaction of light with larger structures composed of atoms and molecules can lead to more complex optical effects. For example, the iridescent colors of a peacock's feathers or a soap bubble result from interference and diffraction, phenomena that occur when light waves overlap and interact. These effects are not due to the absorption or reflection at the atomic level, but rather to the specific arrangement of microscopic structures that cause certain wavelengths of light to constructively or destructively interfere. Understanding color at the atomic level thus requires a multifaceted approach, encompassing the principles of quantum mechanics, thermodynamics, and electromagnetic theory. The behavior of electrons in atoms and molecules, the way they absorb and emit light, and how they interact with thermal energy all contribute to the rich tapestry of colors we perceive. Whether through the selective absorption and reflection of light, the emission of thermal radiation, or the complex interplay of optical effects, the microscopic world of atoms and molecules is the foundation for the vibrant and diverse colors that enrich our everyday experience. Neutron stars and larger cosmic structures. Neutron stars are one of the most fascinating and extreme objects in the universe. Imagine a star that is incredibly dense and compact, so much so that a sugar cube-sized amount of its material would weigh about 1 billion tons on Earth. These stars are often described as colossal atomic nuclei because they are packed with neutrons, the particles found in the nucleus of atoms. Neutron stars form through the process of stellar evolution, which is the life cycle of stars. This life cycle begins with a cloud of gas and dust in space, mostly made up of hydrogen. Under the force of gravity, this cloud collapses, and as it does, it heats up and forms a protostar. When the temperature in the core of this protostar becomes high enough, nuclear fusion starts. Fusion is the process where hydrogen atoms combine to form helium, releasing a lot of energy in the process. This energy is what makes stars shine. For many millions or even billions of years, a star will continue to fuse hydrogen into helium in its core, balancing the inward pull of gravity with the outward pressure from the fusion reactions. However, once the hydrogen in the core is exhausted, the star's life takes a dramatic turn. If the star is massive enough, it begins to fuse heavier elements in a series of stages. First, it fuses helium into carbon and oxygen. Then these elements into even heavier ones like neon and magnesium and so on, all the way up to iron. Iron is unique because fusing it does not produce energy. Instead, it absorbs energy, which makes the star unstable. Once a significant amount of iron builds up in the core, the star can no longer support itself against gravity. This leads to a catastrophic event called a supernova. In a supernova, the outer layers of the star are blown off in an incredibly powerful explosion, while the core collapses under gravity. During this collapse, protons and electrons in the core are squeezed together to form neutrons. This process results in an extremely dense object made almost entirely of neutrons, a neutron star. To give you an idea of just how dense a neutron star is, consider that it has about 1.4 times the mass of our Sun, but is only about 20 kilometers in diameter. This makes neutron stars some of the densest objects in the universe, second only to black holes. The conditions inside a neutron star are unlike anything we can experience on Earth. The density is so high that the structure of atoms is completely broken down. Instead of atoms, there are just neutrons packed closely together. The gravity on the surface of a neutron star is also incredibly strong. If you were to stand on the surface, the gravity would be about 1 billion times stronger than Earth's gravity. This immense gravity also bends light around the star, making it appear distorted to an outside observer. Neutron stars can exhibit some remarkable behaviors. One of the most well-known is that they can spin at incredibly high speeds. When a massive star's core collapses into a neutron star, it retains much of its angular momentum, but because the neutron star is so much smaller, it spins much faster. Some neutron stars, known as pulsars, emit beams of radiation from their magnetic poles. As the neutron star spins, these beams sweep across space like lighthouse beams. If one of these beams points toward Earth, we can detect it as regular pulses of radio waves, hence the name pulsar. Over time, a neutron star will gradually cool and slow its rotation, but this can take millions of years. In some cases, neutron stars can be found in binary systems where two stars orbit each other. If a neutron star has a companion star, it can pull matter from this companion, creating a disk of material around the neutron star. This material heats up and emits X-rays, making these systems very bright in X-ray light. Neutron stars are just one part of the broader tapestry of cosmic structures. They are remnants of stars, but there are also many other fascinating structures in the universe. For example, galaxies are vast collections of stars, gas, dust, and dark matter held together by gravity. Our own galaxy, the Milky Way, contains hundreds of billions of stars, including our Sun. Beyond individual galaxies, the universe is structured into even larger formations. Galaxies are not evenly distributed throughout space. They tend to cluster together in groups and clusters. These clusters can contain hundreds or even thousands of galaxies. Even larger than clusters are superclusters, which are groups of galaxy clusters. The largest structures in the universe are called cosmic filaments and voids. Filaments are vast, thread-like structures of galaxies and dark matter, while voids are large, empty spaces between filaments. Understanding neutron stars and these larger cosmic structures helps us learn about the universe's history and evolution. Neutron stars, with their extreme conditions, offer a natural laboratory for studying physics under conditions that cannot be replicated on Earth. They provide clues about the behavior of matter at nuclear densities, the life cycles of stars, and the dynamics of stellar explosions. In addition to their scientific importance, neutron stars also capture our imagination. They are reminders of the incredible forces at work in the universe and the dramatic ends that stars can meet. The study of neutron stars and the larger structures of the universe is a testament to human curiosity and our desire to understand the cosmos. Through telescopes and space missions, we continue to explore these enigmatic objects, uncovering their secrets and expanding our knowledge of the universe. Atoms in the universe and multiverse theories. Atoms are the basic building blocks of matter, and everything we see around us is made of them. When scientists study atoms, they find a world full of tiny particles and empty spaces. Interestingly, some theories suggest that our universe might resemble an atom in a much larger structure. These ideas often lead to discussions about the multiverse, which is the concept that our universe could be just one of many in a larger system. One theory that draws a comparison between the universe and an atom comes from the idea of scaling. Atoms have a dense nucleus made of protons and neutrons, with electrons orbiting around this nucleus. If you could zoom out far enough, the space between these particles is vast compared to their size. Some scientists imagine that if you could scale up an atom to the size of the universe, it might look similar to our own cosmic structure, with galaxies taking the place of electrons. This idea isn't suggesting that atoms and the universe are exactly the same, but it uses the similarities to help us understand complex concepts. Just like atoms are part of larger molecules and structures, some theories propose that our universe might be part of a much larger system. This is where the idea of the multiverse comes in. The multiverse theory suggests that there could be many universes besides our own. These universes might exist in a vast, higher-dimensional space that we cannot directly see or interact with. Each universe could have different physical laws, constants, and even different types of atoms. Some universes might be similar to ours, while others could be drastically different. One way to think about the multiverse is through the analogy of bubbles. Imagine our universe as a bubble floating in a larger space filled with other bubbles. Each bubble represents a different universe with its own unique properties. Sometimes these bubbles might collide or interact in ways we can't yet understand, possibly leaving subtle clues that we could one day detect. There are several different versions of the multiverse theory. One version comes from the field of cosmology, which studies the origins and development of the universe. According to the inflationary theory, our universe underwent a rapid expansion right after the Big Bang. Some scientists believe that this inflation could have created multiple bubble universes, each with its own set of physical laws. Another version of the multiverse comes from string theory, a theoretical framework that tries to explain all fundamental forces and particles in the universe. String theory suggests that particles are not point-like, but are instead tiny, vibrating strings. In this theory, there could be many different ways to configure these strings, leading to the possibility of numerous different universes, each with its own unique string configuration. Quantum mechanics, the branch of physics that deals with the behavior of very small particles, also provides a basis for multiverse ideas. One interpretation of quantum mechanics is the many-worlds interpretation. This interpretation suggests that every time a quantum event happens, the universe splits into multiple copies, each representing a different outcome of that event. In this view, there could be an almost infinite number of parallel universes, each slightly different from the others. While these theories are fascinating, they are also highly speculative. We currently do not have direct evidence for the existence of other universes. However, the idea of the multiverse raises interesting questions about the nature of reality and our place in it. If there are indeed other universes, what does that mean for our understanding of physics and the cosmos? Scientists are looking for ways to test these ideas. One possibility is to search for evidence of collisions between our universe and others. These collisions could leave detectable imprints in the cosmic microwave background, which is the afterglow of the Big Bang. Another approach is to look for variations in fundamental constants, which might suggest interactions with other universes. The multiverse theory also intersects with philosophical questions. If there are countless other universes, each with different versions of ourselves, what does that mean for concepts like identity and free will? Are we just one of many versions of ourselves, each making different choices in different universes? In the quest to understand atoms, the universe, and the potential multiverse, scientists use advanced tools and technologies. Telescopes, particle accelerators, and supercomputers all play a role in exploring these ideas. For example, the Large Hadron Collider, LHC, at CERN, is one of the most powerful tools we have for probing the fundamental nature of particles and forces. Discoveries made with the LHC could provide insights into whether string theory, and by extension some versions of the multiverse theory, might be correct. Despite the speculative nature of multiverse theories, they push the boundaries of our understanding and encourage us to think beyond the confines of our observable universe. They invite us to imagine a reality that is much larger and more complex than we ever thought possible. Eternal life of atoms. The concept of the eternal life of atoms is deeply rooted in the conservation of matter. This principle states that matter cannot be created or destroyed, only transformed. This means that the atoms making up our bodies and everything around us have been in existence since the beginning of the universe. When we die, our atoms do not simply vanish. Instead, they embark on a remarkable journey, integrating into the ecosystem and continuing to exist in various forms. When a living being dies, the body begins to decompose. This decomposition is a natural process where microorganisms break down complex organic materials into simpler substances. During this process, the atoms that once formed part of the body are released. These atoms can then be absorbed by the soil, taken up by plants, and re-enter the food chain. In this way, the atoms from a single living organism can become part of countless other organisms over time. Consider the journey of a carbon atom in the human body. After death, as the body decomposes, this carbon atom may be released into the soil. From there, it could be absorbed by a plant during photosynthesis, becoming part of the plant's structure. When an animal eats the plant, the carbon atom becomes part of the animal's body. Eventually, when the animal dies, the atom will be released again, continuing its journey through different forms of life. Water is another medium through which atoms travel. The hydrogen and oxygen atoms in the water molecules that make up a significant portion of our bodies are continuously cycled through the environment. After death, the water in our bodies evaporates or is absorbed into the ground, entering rivers, lakes, and the atmosphere. These water molecules can travel great distances, becoming part of different ecosystems and life forms. Nitrogen atoms follow a similar path. They are crucial components of amino acids and proteins. After death, nitrogen atoms are released into the soil, where bacteria convert them into forms that plants can absorb. These plants are then consumed by herbivores, and the nitrogen atoms become part of new proteins in these animals. This cycle repeats endlessly, demonstrating the incredible resilience and continuity of atoms in nature. The eternal life of atoms extends beyond the biological realm. Atoms are also involved in geological processes, such as the formation of rocks and minerals. For instance, silicon and oxygen atoms in the Earth's crust form quartz, a common mineral. Over millions of years, geological processes like erosion and volcanic activity can redistribute these atoms, incorporating them into different rocks and landscapes. Subatomic particles, the building blocks of atoms, also exhibit a kind of eternal life. Protons and neutrons, which make up the nucleus of an atom, are composed of even smaller particles called quarks. These particles are held together by the strong nuclear force, one of the fundamental forces of nature. While atoms can be broken apart during nuclear reactions, the quarks within protons and neutrons remain bound together, suggesting a form of permanence at the subatomic level. Electrons, the particles that orbit the nucleus of an atom, also exhibit remarkable stability. In typical conditions, electrons do not decay or disappear. They may be transferred between atoms during chemical reactions, but they continue to exist indefinitely. This enduring nature of subatomic particles underlies the stability of matter itself. Hypotheses about the eternal life of subatomic particles have fascinated scientists for decades. One such hypothesis involves the concept of particle-antiparticle pairs. According to quantum mechanics, particles can spontaneously appear and disappear in pairs. These virtual particles exist for extremely short periods before annihilating each other. This phenomenon suggests that the universe is teeming with activity at the subatomic level, with particles constantly being created and destroyed, yet the overall balance of matter remains unchanged. Another intriguing hypothesis is based on the idea of proton decay. Some theories in particle physics suggest that protons, which are incredibly stable on human timescales, might eventually decay over vast periods. If true, this would imply that even the fundamental building blocks of matter are not truly eternal. However, proton decay has not been observed, and the timescales proposed are so long that they exceed the current age of the universe by many orders of magnitude. The fate of atoms and subatomic particles is also tied to the ultimate fate of the universe. In the far future, the universe may undergo different phases depending on its expansion and the forces at play. One possibility is the heat death of the universe, where all matter and energy are evenly spread out, and no thermodynamic work can be performed. In such a scenario, atoms might break down into their constituent particles, which would continue to exist in a cold, dark universe. Alternatively, the universe might collapse in a big crunch, where all matter is pulled back into a hot, dense state. In this extreme condition, atoms would be destroyed, and subatomic particles might merge into new forms of matter. Another possibility is the Big Rip, where the universe's expansion accelerates to the point that it tears apart galaxies, stars, planets, and even atoms. In each of these scenarios, the fundamental particles would still exist, albeit in vastly different conditions than we observe today. The eternal life of atoms and subatomic particles reflects the conservation of matter principle, highlighting the incredible journey these tiny building blocks undergo. From forming the structure of living organisms to becoming part of the Earth's geology, atoms are continually recycled through various processes, maintaining their presence in the universe. While the specific fate of these particles remains a topic of scientific investigation, their enduring nature underscores the interconnectedness and continuity of all matter in the cosmos. Dark matter and dark energy. Dark matter and dark energy are two of the most mysterious and fascinating components of our universe. They do not interact with light or any other form of electromagnetic radiation, making them invisible and detectable only through their gravitational effects. Despite being unseen, they play crucial roles in shaping the universe and influencing the behavior of atoms. Dark matter is thought to make up about 27% of the universe. Unlike normal matter, which includes atoms and everything we see around us, dark matter does not emit, absorb, or reflect light. This makes it completely invisible and detectable only through its gravitational influence on visible matter. Scientists first proposed the existence of dark matter when they observed that galaxies were rotating much faster than expected based on the amount of visible matter they contained. The gravitational pull from the visible matter alone could not account for the observed speeds. suggesting that an unseen mass was contributing to the gravitational force. One way scientists study dark matter is by looking at the motion of stars within galaxies. If only the visible matter were present, the stars at the edges of galaxies would orbit much more slowly than they do. However, observations show that these stars move at high speeds, implying the presence of a significant amount of unseen matter providing the necessary gravitational pull. This unseen matter is what we call dark matter. Dark matter is also studied through gravitational lensing, a phenomenon where light from distant objects is bent around massive objects like galaxies. The amount of bending can tell scientists how much mass is present, including both visible and dark matter. Observations of galaxy clusters, which are groups of galaxies held together by gravity, show much more mass than can be accounted for by visible matter alone, further supporting the existence of dark matter. While we know dark matter exists due to its gravitational effects, its exact nature remains a mystery. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, and axions, but so far no direct detection has been made. Experiments around the world are trying to detect these particles, and scientists are hopeful that future advancements will provide more answers. Dark energy is even more mysterious than dark matter. It is believed to make up about 68% of the universe and is responsible for the accelerated expansion of the universe. Unlike dark matter, which pulls objects together through gravity, dark energy seems to push objects apart. The discovery of dark energy came from observations of distant supernovae in the late 1990s. Scientists expected that the expansion of the universe would be slowing down due to the gravitational pull of all the matter in the universe. Instead, they found that the expansion was speeding up, suggesting the presence of a repulsive force, dark energy. The nature of dark energy is still unknown, but several theories have been proposed. One possibility is that dark energy is a property of space itself. According to Einstein's theory of general relativity, space can have its own energy, and as the universe expands, more space means more dark energy, causing the expansion to accelerate. Another theory is that dark energy is related to the quantum field that fills space, known as the vacuum energy. However, the amount of vacuum energy predicted by quantum physics is much larger than what is observed, leading to what is known as the cosmological constant problem. The presence of dark matter and dark energy has significant implications for the fate of the universe. If dark energy continues to drive the accelerated expansion, the universe could eventually reach a state where galaxies are so far apart that they can no longer interact with each other. This scenario is known as the Big Freeze, where the universe becomes a cold, dark, and empty place. Alternatively, if dark energy changes over time, it could lead to a Big Rip, where the expansion becomes so rapid that it tears apart galaxies, stars, and even atoms. Understanding dark matter and dark energy is crucial for a complete picture of the universe. They not only influence the large-scale structure of the cosmos, but also play a role in the behavior of galaxies and the formation of stars. The study of these invisible forces is a frontier in modern astrophysics, requiring innovative techniques and advanced technology. Dark matter, for instance, influences the formation and evolution of galaxies. Without dark matter, galaxies might not have enough gravitational pull to form and hold together. The extra mass provided by dark matter helps galaxies to clump together and grow. This process began in the early universe, shortly after the Big Bang, when dark matter clumped together under its gravity, creating the seeds for galaxies to form. Dark energy, on the other hand, affects the universe on the largest scales. Its influence becomes more apparent as the universe expands, driving galaxies further apart. This expansion counteracts the pull of gravity and affects the overall shape and fate of the universe. The study of cosmic microwave background radiation, which is the afterglow of the Big Bang, provides clues about the distribution of dark matter and dark energy in the universe. By analyzing this radiation, scientists can infer the composition and behavior of the universe over billions of years. The search for dark matter and dark energy is ongoing, with experiments both on Earth and in space. Telescopes and observatories, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, are crucial in observing distant galaxies and supernovae to understand the effects of dark energy. Particle detectors deep underground and in space are designed to detect dark matter particles directly, although these particles have so far eluded capture. The pursuit of knowledge about dark matter and dark energy represents one of the most exciting and challenging endeavors in modern science. These invisible influences shape the universe in profound ways, and uncovering their secrets will help us understand the fundamental nature of reality. The journey to discover what dark matter and dark energy are made of and how they work is a testament to human curiosity and the drive to explore the unknown. Quantum entanglement. Quantum entanglement is one of the most mysterious and fascinating phenomena in the world of physics. Albert Einstein famously referred to it as spooky action at a distance because it seemed to defy the conventional understanding of how objects interact. This phenomenon occurs when two particles become linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. To understand quantum entanglement, we first need to delve into the basics of quantum mechanics, the branch of physics that deals with the behavior of very small particles like atoms and electrons. In the quantum world, particles can exist in multiple states at once, a property known as superposition. For example, an electron can spin in multiple directions simultaneously until it is observed or measured. When two particles become entangled, their properties become intertwined. This means that the state of one particle is directly related to the state of the other. If you measure the state of one particle, you instantly know the state of the other, even if they are light years apart. This instant connection happens without any signal passing between the particles, which is what puzzled Einstein and other physicists. One of the key experiments that demonstrated quantum entanglement was conducted by physicist Alain Aspect in the early 1980s. Aspect and his team used pairs of entangled photons, particles of light, and measured their polarization, which is the direction in which the photon's electromagnetic waves oscillate. According to classical physics, information about the state of one photon should not affect the other if they are far apart. However, the results showed that the measurements were correlated in a way that could not be explained by classical theories. This confirmed that the photons were indeed entangled, and that their states were linked regardless of the distance between them. The implications of quantum entanglement are profound. It challenges the traditional notion of locality, which states that objects are only influenced by their immediate surroundings. In the classical world, information cannot travel faster than the speed of light. However, entanglement suggests that there is a form of connection that transcends this limit, though it does not allow for faster-than-light communication. Quantum entanglement is not just a theoretical curiosity. It has practical applications in the emerging field of quantum computing and quantum communication. In quantum computing, entangled particles can be used to perform complex calculations at speeds far beyond those of classical computers. Quantum bits, or qubits, can exist in multiple states simultaneously, allowing quantum computers to process a vast amount of information at once. Entanglement enables qubits to be correlated in a way that can solve certain problems much more efficiently than traditional computers. In quantum communication, entanglement can be used to create highly secure communication channels. One proposed method is quantum key distribution, where entangled particles are used to generate a shared secret key between two parties. Any attempt to eavesdrop on the communication would disturb the entangled particles, revealing the presence of an intruder and ensuring the security of the transmitted information. The phenomenon of quantum entanglement also raises philosophical questions about the nature of reality. In the quantum world, particles do not have definite states until they are observed. This leads to the idea that observation itself plays a crucial role in determining the state of a system. The act of measurement seems to collapse the superposition of states into a single definite state. This challenges our classical understanding of an objective reality that exists independently of observation. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, proposed a thought experiment known as the EPR paradox to highlight the seemingly paradoxical nature of quantum entanglement. They argued that if quantum mechanics were correct, it would imply that information could travel instantaneously, violating the principle of locality. They believed that quantum mechanics was incomplete and that there must be hidden variables that determine the states of particles. However, subsequent experiments, including those by John Bell and Alain Aspect, have shown that no hidden variable theories can fully explain the correlations seen in entangled particles. Despite its mysterious nature, quantum entanglement is a well-established and experimentally verified phenomenon. It is an integral part of the standard model of quantum mechanics, which accurately describes the behavior of particles at the smallest scales. Scientists continue to explore the implications of entanglement and its potential applications, pushing the boundaries of our understanding of the quantum world. Research into quantum entanglement has led to the development of new technologies and theoretical insights. For instance, quantum teleportation, a process that uses entanglement to transfer the state of one particle to another without moving the particle itself, has been experimentally demonstrated. While this is not teleportation in the science fiction sense, it represents a significant step forward in quantum information science. Furthermore, entanglement plays a crucial role in understanding other quantum phenomena, such as quantum coherence and quantum interference. These effects are essential for the functioning of quantum computers and other quantum technologies. Scientists are also investigating the role of entanglement in biological systems, exploring how it might influence processes such as photosynthesis and bird navigation. The study of quantum entanglement has also led to new theoretical developments, such as the concept of entanglement entropy, which measures the amount of entanglement in a system. This has implications for understanding the behavior of complex quantum systems and the nature of black holes and the information paradox. As research continues, quantum entanglement remains one of the most intriguing and challenging areas of physics. It defies our classical intuitions and opens up new possibilities for technology and our understanding of the universe. The exploration of this spooky action at a distance continues to captivate scientists and philosophers alike, promising to reveal even deeper insights into the fundamental nature of reality. Atoms and the origins of life. Atoms are the building blocks of everything in the universe, including life itself. To understand the origins of life, we must first look at the atoms and molecules that make up living organisms. Life as we know it is based on a handful of essential elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements combine in various ways to form the complex molecules necessary for life. The journey of these atoms began billions of years ago in the heart of stars. Through the process of nuclear fusion, stars create heavier elements from lighter ones. When massive stars reach the end of their life cycles, they explode in supernovae, scattering these elements across the universe. This stellar dust contains the raw materials for planets and eventually for life. On Earth, the conditions were just right for these atoms to come together and form life. Around 4.5 billion years ago, our planet formed from a cloud of gas and dust left over from the Sun's formation. During its early years, Earth was a molten mass, bombarded by meteorites and comets. These impacts brought not only more elements, but also water, a crucial ingredient for life. As Earth cooled, its surface solidified and water began to accumulate in oceans. In these primordial waters, the basic building blocks of life started to form. Simple molecules containing carbon and hydrogen, such as methane, could combine with nitrogen, oxygen, and other elements to form more complex molecules like amino acids and nucleotides. These molecules are the precursors to proteins and DNA, the essential components of all living cells. The exact process by which these molecules came together to form the first living organisms remains one of science's greatest mysteries. Several theories exist, but the most widely accepted is the idea of a primordial soup. This theory suggests that early Earth's oceans were filled with a rich mixture of organic molecules. Energy from the sun, lightning, and volcanic activity triggered chemical reactions among these molecules, gradually leading to the formation of more complex compounds. One famous experiment that supports this theory was conducted by Stanley Miller and Harold Urey in 1953. They simulated the conditions of early Earth in a laboratory, mixing water, methane, ammonia, and hydrogen, and then zapping the mixture with electric sparks to mimic lightning. After a week, they found that several amino acids had formed, showing that the basic building blocks of life could arise from simple chemical reactions. Once these building blocks were in place, the next step was for them to assemble into the first primitive cells. One key component of cells is the membrane, which is made of lipids. Lipids can spontaneously form structures called micelles and vesicles when mixed with water. These structures can trap other molecules inside, creating a protected environment where further chemical reactions can occur. This could have been a crucial step in the formation of the first living cells. Inside these primitive cells, the complex molecules of life could interact in increasingly sophisticated ways. DNA and RNA, which store and transmit genetic information, likely played a vital role. RNA in particular is thought to have been crucial in the early stages of life. It can both store genetic information and act as a catalyst for chemical reactions, a role usually played by proteins. This has led to the hypothesis of an RNA world, where RNA molecules were the first self-replicating systems, eventually leading to the development of DNA and proteins. As these early cells evolved, they began to harness energy from their environment. One way they did this was through photosynthesis, a process that uses sunlight to convert carbon dioxide and water into glucose and oxygen. Photosynthesis not only provided a new source of energy, but also produced oxygen, which gradually accumulated in Earth's atmosphere. This increase in oxygen allowed for the development of more complex life forms that rely on oxygen for respiration. Over billions of years, these simple, single-celled organisms evolved into the diverse array of life we see today. The atoms that once floated in space as part of a star now make up every plant, animal, and human being on Earth. The same basic chemical principles govern all life, from the simplest bacteria to the most complex multicellular organisms. The study of life's origins is not just about understanding the past, it also has implications for the search for life beyond Earth. If life arose from basic chemical reactions here, it could potentially arise on other planets with similar conditions. Scientists are exploring the possibility of life on Mars, in the subsurface oceans of Jupiter's moon Europa, and on Saturn's moon Enceladus. These places have water and the necessary chemical elements, making them prime targets in the search for extraterrestrial life. Understanding the origins of life also has practical applications here on Earth. By studying how life's building blocks form and interact, scientists can develop new medical treatments, create more sustainable agricultural practices, and even develop new materials and technologies. The field of synthetic biology, which involves designing and constructing new biological parts and systems, draws heavily on the principles learned from studying life's origins. The story of atoms and the origins of life is a testament to the power of chemistry and the incredible potential of the elements that make up our world. From the heart of stars to the depths of the ocean, these atoms have journeyed across the cosmos, coming together to create the wonder of life. As we continue to explore and understand this process, we gain a deeper appreciation for the complexity and beauty of the natural world and our place within it. Atoms in extreme environments. Atoms are the fundamental building blocks of matter, forming everything we see around us. But in extreme environments like neutron stars and black holes, the behavior of atoms is pushed to unimaginable limits. These environments provide a unique perspective on the resilience and transformation of matter under extreme conditions. Neutron stars are one of the densest objects in the universe, formed from the remnants of massive stars that have exploded in supernovae. When a star much larger than our Sun reaches the end of its life, it can no longer sustain the nuclear reactions that have kept it burning. The core collapses under the force of gravity, compressing protons and electrons into neutrons and creating a neutron star. In a neutron star, the density is so extreme that a sugar cube-sized amount of its material would weigh about 1 billion tons on Earth. Atoms as we know them cannot survive in such conditions. The intense gravity crushes electrons into protons, forming neutrons. These neutrons are packed together tightly, so much so that they form a superfluid, a state of matter that flows without friction. The surface of a neutron star is thought to be a thin crust of normal atomic nuclei and electrons. However, just a few hundred meters below the surface, the pressure is so high that these nuclei are crushed together and the electrons are forced into the nuclei, forming neutrons. This creates a unique environment where matter exists in a state that cannot be found anywhere else in the universe. Further inside the neutron star, the density increases even more. Here, neutrons are packed together so tightly that they start to overlap, and their individual identities begin to blur. This creates a neutron superfluid that is incredibly stable and can conduct heat and electricity with perfect efficiency. At the center of a neutron star, the conditions are even more extreme. Theoretical models suggest that the pressure and density may be so high that neutrons themselves break down into their constituent quarks. This could create a core of quark matter, a substance even denser than neutron matter. However, this is still a topic of active research, and scientists continue to study these extreme conditions to better understand the behavior of matter under such intense pressures. Black holes represent an even more extreme environment. Formed from the collapse of massive stars, black holes have gravitational fields so strong that nothing, not even light, can escape from them. The boundary around a black hole, known as the event horizon, marks the point beyond which anything that crosses can never return. Inside a black hole, the laws of physics as we know them break down. The singularity at the center of a black hole is a point of infinite density, where the gravitational pull is infinitely strong. In such an environment, atoms are completely torn apart. The intense gravity stretches and compresses matter to such an extent that it is no longer recognizable. Around the event horizon, matter spirals inwards, forming an accretion disk. In this disk, atoms are subjected to intense gravitational forces, causing them to move at incredibly high speeds and collide with each other. These collisions generate immense heat, causing the matter to emit high-energy radiation such as X-rays. This radiation can be detected by telescopes and provides valuable information about the behavior of matter near black holes. The environment near a black hole is so extreme that it challenges our understanding of physics. For example, time behaves differently near a black hole. Due to the intense gravitational field, time appears to slow down relative to an outside observer. This phenomenon, predicted by Einstein's theory of general relativity, has been confirmed by observations and provides a fascinating glimpse into the effects of extreme gravity on the fabric of space-time. Scientists use advanced simulations and observations to study the behavior of atoms and matter in these extreme environments. Telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory have provided images and data that help researchers understand the processes at work. Additionally, gravitational wave detectors like LIGO have observed the mergers of neutron stars and black holes, providing further insights into these exotic objects. One of the most intriguing questions is what happens to matter that falls into a black hole. According to current theories, it is crushed into an infinitely small point at the singularity. However, some scientists propose that the matter could be transformed into a new state, or even ejected into another part of the universe through hypothetical structures called wormholes. These ideas remain speculative and are at the forefront of theoretical physics research. The study of atoms in extreme environments like neutron stars and black holes not only helps us understand the behavior of matter under extreme conditions, but also provides insights into the fundamental laws of physics. These objects are natural laboratories for testing the limits of our theories and discovering new phenomena. As our technology and observational capabilities improve, we continue to learn more about these mysterious objects. Future missions, such as the James Webb Space Telescope and more advanced gravitational wave detectors, promise to provide even more detailed observations. These advancements will help us uncover the secrets of neutron stars and black holes and deepen our understanding of the universe. The exploration of neutron stars and black holes pushes the boundaries of human knowledge and imagination. These extreme environments challenge our understanding of the fundamental nature of matter and the universe. By studying them, we gain a deeper appreciation of the resilience and adaptability of atoms and the incredible diversity of the cosmos. As we continue to explore these cosmic frontiers, we are reminded of the boundless potential of scientific discovery and the enduring mystery of the universe. The search for exotic atoms and particles. The search for exotic atoms and particles is one of the most exciting and challenging areas in modern physics. These unusual forms of matter, unlike anything we encounter in everyday life, can provide crucial insights into the fundamental nature of the universe. Scientists around the world are engaged in experiments and theories to uncover and understand these exotic entities. Exotic atoms are a type of atom where one or more of the standard particles are replaced by other particles. A well-known example is the muonic atom, where one electron is replaced by a muon. Muons are similar to electrons but are much heavier. Because of their greater mass, muons orbit much closer to the nucleus than electrons do. Studying muonic atoms allows scientists to make precise measurements of the properties of the nucleus and the fundamental forces at play. Another type of exotic atom is the positronium atom. Positronium consists of an electron and its antimatter counterpart, a positron, bound together in a sort of miniature solar system. This atom is highly unstable because when the electron and positron meet, they annihilate each other, releasing energy in the form of gamma rays. Despite its short life, positronium is useful for studying matter-antimatter interactions and the properties of antimatter. The search for exotic particles often focuses on those that are predicted by theories but have not yet been observed. One of the primary locations for this search is the Large Hadron Collider, LHC, at CERN in Switzerland. The LHC is the world's largest and most powerful particle accelerator, capable of smashing particles together at nearly the speed of light. These high-energy collisions can create conditions similar to those just after the Big Bang, potentially producing exotic particles. One of the most significant discoveries at the LHC was the Higgs boson in 2012. The Higgs boson is a particle associated with the Higgs field, which gives other particles their mass. This discovery was a major milestone, confirming a key part of the standard model of particle physics. However, the standard model is not the final word on particle physics. It cannot explain dark matter, dark energy, or the full range of particle masses. This suggests the existence of new, exotic particles beyond those currently known. Supersymmetry is one theoretical framework that predicts the existence of exotic particles. According to supersymmetry, every particle in the standard model has a partner particle with different properties. These supersymmetric particles, or sparticles, could help explain the nature of dark matter, among other mysteries. Despite extensive searches, no sparticles have yet been detected, but the hunt continues with ever more sensitive experiments. Neutrinos are another area of intense interest. These nearly massless particles are incredibly difficult to detect because they interact very weakly with matter. Billions of neutrinos pass through us every second without any noticeable effect. Neutrino research has revealed that these particles have a small mass and can oscillate between different types, or flavors. Understanding neutrinos better could provide insights into the asymmetry between matter and antimatter in the universe. Antimatter itself is a form of exotic matter that has captivated scientists for decades. Every particle has an antimatter counterpart with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other, releasing energy. The apparent scarcity of antimatter in the universe is one of the great mysteries in physics. Experiments like those conducted at the Alpha Magnetic Spectrometer on the International Space Station aim to detect antimatter in cosmic rays, which could provide clues about this imbalance. So, what's your conclusion? I'd be interested to hearing it. Make sure to subscribe to the channel and let me know.